Hello students, thank you for joining me once again on this little journey of ours. Today we're going to be discussing something that I hold very near and dear to my heart. It's an aspect of physics that I truly find interesting in every nook I've managed to investigate it. And the topic, of course, is energy. Now, energy is, by and large, the most mystical of concepts in physics. It has inspired many different works of fiction, everything from superheroes to fantastical auras that surround you and give you some sort of spiritual significance and empowerment. It is also the core of physics. Energy is, by every stretch of the imagination, a embodiment of, I would say, all of physics. It all starts here. And so I thought that it would be very fitting to start our journey here. Now, given that some of you have already seen some of this before, but many of you haven't, I think it will be of great use to simply go over the basics in this video, and then I'll extend into some very interesting problems over the course of the next week. So, a good place to start is to define exactly what energy is from a physicist's point of view. And I would say the most pragmatic, perhaps not the most rigorous, but the most pragmatic definition of energy is a quantity that is conserved in a closed system. So we have three key things that we need to look at with this definition. Although it may look a little boring at first, this actually gives us quite a bit of information that we will need to understand how energy works in physics. A quantity is, of course, a number, or in many cases, a function that will describe our objects in our system in terms of some of the qualities that they have. This quantity, or function rather, will define everything that we need to know about that object's motion if we know enough about the system. And this quantity, this function, it is conserved in whatever closed system it is. I think it would be best to start next with the closed system part of it. A closed system is exactly what you would probably imagine. It is something that is contained in such a way that none of the elements outside of it can affect it. The biggest example would be, of course, our universe. Our universe is experimentally very seemingly a closed system. We've seen no indication that it isn't. And we try our very hardest as physicists to make our labs closed systems and our experiments closed systems. We don't want anything interfering with what we're seeing. This can be incredibly challenging at times, but thankfully many brilliant minds have become very good at creating closed experiments. And lastly, we have this idea of conservation. Now, you've likely heard of the phrase conservation of energy, and it's sort of built into the definition of what energy is. If you have a system that is closed, then all of the energies in the system, while they may change from one thing into another, energy is never lost. That is an important and valuable tool for all of physics, is that the energy can change, it can manipulate, it can fold, it can bend, but it can never go away. And most importantly, you cannot create it out of nothing. Energy cannot spontaneously appear within your closed system. Now, knowing all this, let's talk a little bit about what kind of forms energy can take. So we know that, of course, there is energy involved with motion, and we can call this kinetic energy. Every time you've hit your fist against a desk, every time you've run into some sort of rock on the ground and made yourself fall over, every time you've driven in a car, you've felt whatever latent energies of your body transitioning into motion. And so we call this form of energy kinetic energy, and it is proportional to the square of your speed. Now, this symbol for proportionality it simply means that whatever you have on the other side of the equation is the same as what's on the left side of the equation, multiplied by some number. And what that number is in this case would be 1/2, my goodness, the mass of the object times the velocity squared. So you see here, we've went from being proportional to the velocity squared to being exactly equal to 1/2 the mass times velocity squared. This is our constant of proportionality. Just a little bit of math knowledge for those of you who may not have ever taken a course like this. So knowing what we have here, I think it's safe to say that we can then begin talking about perhaps something that's a little bit more abstract. Let us simply start with the name of this type of energy, and I'll try to explain it as best I can as we go along. And it's called potential energy. Now, potential energy takes many different forms, but what it generally describes is, as you might imagine, the unattained potential to create something. Now, that something could very well be movement, it could be some sort of chemical reaction, it could be heat. There are several different types of potential energies that relate to several different forms of energy. For instance, we can have gravitational potential energy. That's usually the first one you talk about. The second one is usually electrical potential energy. There is, of course, spring potential energy, or harmonic potential energy. There is, of course, chemical potential energy, which you'll sometimes learn about in a chemistry class. And then there's a thermal potential energy. So many different ways of existing in this sort of latent state of energy, this state where you are being compelled to move or change in some way. Knowing all this, it is very difficult to describe this mathematically without getting just a little bit of calculus thrown into the mix. And so I will try to describe to you a little bit mathematically about what potential energy actually is in terms of mathematics. If we consider 2 points, and let us say that someone or something follows a path along these 2 points in free space, and that they start from rest. V in this case is speed, and or rather, let's make it a vector. Velocity, and that velocity is 0 to start with. With this in mind, what we can think of is, how did he go from one place to the other? Well, let's say that there wasn't a road to walk on or some engine to get him there. Let's say this person or thing was simply compelled to move by some strange force pulling on them. Well, that force directs that person across this path. And as that person moves along that path, he experiences something called work. Work is a concept that is directly related to energy. The units are the same. They're both calculated in joules. That is their unit of measurement that we typically like to use in introductory physics. And to calculate the work done across this path, there will be some sort of differential element of displacement at each point, and there is, of course, a force compelling it across this point. And this work is, of course, simply the integral of the force along the path of displacement. Now, this integral can be kind of intimidating if you've never seen something like that before. But I'll try to describe it qualitatively as best I can for those of you who have never taken calculus before. Imagine that each individual point along this path has some vector associated with it, telling you the direction of the path at that point. We call that vector dx, which is a differential element of that curve. As you follow this curve, there is obviously a force acting on you at every given point along that curve. And what this does is it says, okay, let's take the force vector along this path and the differential element of that path and project them onto each other in such a way that they produce a number. Now, exactly how that operation is performed is a question for a calculus book. If any of you would like to see me describe that in more detail, I'd be more than happy to. In fact, Calc 3 is actually one of my favorite subjects to teach. And what this integral symbol here does, this little curly s, is it says we're going to add up each of those projections along this entire path to form a complete picture of something happening in that path. In this case, the work. The work is, of course, measured in joules, which is, of course, the same as energy. And there are some things that we can say about the work that is done in this case. Of course, if the person moves along this path, say by an engine or through the means of their feet, then there really isn't that much to say about a potential energy. However, imagine for a second that this is a bowling ball, and it's, for some bizarre reason, floating in Jupiter's orbit. It will either, if it has angular momentum, go around Jupiter, or it will descend into Jupiter through its gravitational attraction. This gravitational attraction is described by the vector field associated with Jupiter. Every mass in the universe seems to produce this field, this vector field around it, that tells things in its presence with the property of mass, move this way. Just do it. Go there now. That's exactly what gravity is telling seemingly everything with mass in the universe. And everything is constantly communicating with each other. This vector field is a very real thing. It is a physical thing. For instance, an electric or magnetic field can quite literally bump you on the head. It is something that can happen. And so these things, which we call vector fields, are true physical things. And in order to describe vector fields effectively, it's useful to talk about something that is a little bit more advanced than what you talk about in introductory physics, but the idea of being a conservative vector field. There's that word again, conservative. A vector field is conservative when no matter what path you take along a path in it, as you're being compelled by it, the total work done is the same. This is in effect a statement of conservation of energy. It says that no matter how you change your energy along some sort of path, the total work you do will be identical regardless. And of course, not all processes are conservative. In that case, many times energy will be lost as heat. But ultimately, whenever you are moving in the space of an electrical field, a magnetic field, or, I'm sorry, not a magnetic field, but an electric field or a gravitational field, it doesn't matter what path you move along two paths, you'll always do the same amount of work. That's useful. And this vector field that exists, that compels you to move, assume that you're sitting stationary with respect to these 2 points, even though you want to move along this path. That capacity to want to move is potential energy. And as far as the mathematical objects that describe vector fields, well, in the case of a conservative vector field, you start with something appropriately called a potential. Potentials are arguably more fundamental than vector fields. I'll discuss an experiment later in which we can show that a magnetic vector potential actually has some impact on a system when its magnetic field can't. And those are all very important experiments to be done. And a lot of the basic ideas in physics that become very challenging to people start here. A potential is something very similar to a vector field, except it is not a vector associated function. It is a scalar function, which means it seemingly exists in all of space, but it exists merely as something that is there in the space around an object, and it doesn't dictate by itself the vectors of it. Its gradient is what determines that sort of vector field. Now, I've just used a word that may be quite alien to some of you, gradient. After all, I'm trying to make this as qualitative as possible. With a potential, whenever you have it around the space of an object, say an electric charge or a planet, if you look at how the potential changes with respect to, say, the distance away from an object or the rate at which an object is spinning, if you always look at the rate that the potential is changing, it will give you the vector field associated with that object, and it will tell you the potential energy as well. To find the potential energy from the potential, oftentimes in introductory physics at least, you merely need to multiply by a constant of Q. In fact, no, I actually believe even in intermediate that's pretty much always the case. Whenever you have the potential, you can get the potential energy simply by multiplying it by the quality of the quantity of the other object. And so I will end our conversation with one little note, and that is that there is one more kind of energy that we need to consider here, and that is heat. Heat is a rather cumbersome thing to deal with. It is something that is very easy to create, especially for life, and it is incredibly difficult to convert back into something like potential energy. It is actually not too terribly difficult to turn it into kinetic energy. In fact, that is how we power most of our power plants. The heat generated from steam powers a turbine that will spin and produce electrical power for the grid. And so heat is incredibly useful and it's incredibly important, but you don't really talk about it much in introductory physics because it is a little bit difficult to work with mathematically. You have to have a bit more of an understanding of thermodynamics before you can get into it, and that is often relegated to the third course in physics. And with that, thank you all so much for watching. I appreciate your time and your attention. Please come back another time. Don't forget to like and subscribe my video if you enjoyed it. And I will see you soon. Thank you very much.